Welcome. We are looking at the phase field equation. We said that the phase field modeling actually incorporate the interfacial energy. So, it is very important to understand where the interfacial energy is coming from in this model. So, that is what we want to understand in this part of this lecture. So, let us consider the free energy, the bulk free energy density that we were looking at. So, it had a 0, it had a minima at 0, it had a maxima at 0.5 and it had another minima at 1. Right. This is 0, this is 1, this is 0.5. Okay. Now, consider a system which is what we are going to solve. Okay. So, it has this to be the A rich region, this to be the A rich region, this to be the B rich region. So, I am going to start with a profile. So, if you look at the initial profile, it will look like that. Remember, this is consistent with periodic boundary condition. Okay. So, this is the profile that I start. In the case of a Cahn-Hilliard equation, you saw that the profile is going to set up like this. So, it is going to become like this. Now, if you look at what happens in this profile, let us look at a bulk region. What happens in the bulk region? This is our free energy. We said it is F0 plus kappa del C squared dV, right. So, this is what we were looking at. Now, in this region, because I have taken my minima to be here at 0. So, when the composition is 0, that is 0, and this F0 which is nothing but A C squared into 1 minus C whole squared, this becomes 0 at C equal to 0. And because there are no gradients, because composition is uniform here, del C is 0, so the F is 0. So, in pure bulk A rich region, the free energy is 0. In a similar fashion, if you look at where composition is 1, you can see that the F is again 0, because 1 if you substitute in 1 minus C whole squared, that term is going to become 0. Again there are no concentration gradients, so that is also going to be 0. In the region where it changes from either 0 to 1 or 1 to 0, there are two contributions that are coming. One contribution is that the bulk free energy, which is this contribution, is going to increase, because you are going to sample points with all this composition, right. Any region with this bulk composition will have higher free energy as compared to this. So, this is going to have a higher energy. Because remember, I mean, this is the barrier and this barrier height was decided by A, it is A by 16, because if you put 0.5 here, it is 0.5 squared into 0.5 whole squared. So, it is 0.5 whole power 4, that is 1 by 2 power 4. So, A by 2 power 4, A by 16, that is the barrier height. So, it is going to get to sample these regions. So, suppose if this composition changes abruptly, suppose I can keep up to this as 1, up to this as 0, and then the composition changes abruptly, then the contribution from this will be very low, because it will be 0, but the del C term, which is the gradient term, is going to become infinity. So, when this is 0, this becomes infinity. On the other hand, one can say that from this point to this point, okay, the composition, right, what have I done? I have made the del C as small as possible. So, the contribution from this part is going to become very low, but because now it is looking at compositions of all these points, most of the points are away from the minima. So, there is going to be huge contribution that is going to come from the bulk free energy density. Okay. So, now that contribution is going to become very large. So, the system is going to adjust the del C, the gradient in composition, in such a way that most of it will keep it here, because this is also 0, this is also 0, but it has to support an interface from a B rich region and an A rich region. So, in that region it is going to choose that del C, which as compared to this will minimize the energy. So, if it takes very small del C, then it will have large contribution from here. If it takes very large del C, this contribution will be lower, but the del C contribution itself will be high. So, the system chooses an interface which will be an optimum of these two. In other words, the A in this F0 and kappa here in the del C term together determine what is the interfacial energy. Now, thermodynamically the interfacial energy is the excess free energy. So, how do we define? We define it as the free energy of a system which has just this A and just this B. You add them up, you subtract from a system which has these interfaces. Now, we have two interfaces, so it will be the interfacial energy will be 2 times the interfacial energy. Okay. So, but we know that for the bulk we have set up the free energy to be 0. So, if you measure this quantity integral of F0 plus k del C squared for a system which develops these interfaces, that is the excess free energy associated with the interface itself, because if I had taken all A or all B, then I would have gotten 0 from this. So, now because I have some part A and some part B, the interface forms and the excess free energy associated with the interface is just obtained by the evaluation of this free energy. So, that is what we want to do now, and in this case I do not want to take a initial profile which is sinusoidal, but I want to take an initial profile which looks like this. That is the code that I have. So, let us take the FFT Conn-Hilliard code that we had, call this Conn-Hilliard FFT dot oct. So, I am going to say interfacial energy Conn-Hilliard dot OCT vi interfacial energy Conn-Hilliard. So, I am going to take it on a bigger system, okay, and I am going to change the initial profile. So, I do not want any m. So, I am going to make the initial profile like this for I equal to n by 4 plus 1. That means what? Quarter to 3n by 4, 3 quarters. I am going to say Ci is 1, and so for the first quarter and the last quarter I am going to make the composition to be 0. So, I want to first define C is equal to zeros of n comma 1. So, I have 128. So, I have defined a composition which will be vector with 128 zeros, of which the first quarter and last quarter I am going to leave it as 0, but the middle half I am going to put as 1. So, this is the initial profile. Okay. So, we plot the initial profile, we evolve the system, and now we need to run for long time because we want to achieve equilibration, and once we get that, so we get to the solution, we plot the final solution. After this is where I want to calculate the energy. Now, energy calculation means that we need to calculate A C squared into 1 minus C whole squared plus kappa del C whole squared at every point, and you add that up. So, that is basically the excess free energy itself, because for the bulk phases the free energy is 0. If I integrate this quantity, that will be the bulk free energy itself. So, that is what I want to do now. To do that, now I know the final composition profile. So, I am going to do the Fourier transform of composition. I will tell you why I do this FFT of C, okay, and I implement the periodic boundary condition stuff. So, I am going to take these 4-5 lines, I am going to put there. So, I am going to put the 5 lines here. So, I am going to implement periodic boundary condition. For doing what? I am going to take the C hat is equal to complex 0 comma 1 multiplying k multiplying C hat of I, okay, and for. Okay. So, what is being done here? See, I want to calculate the concentration gradient, because I can do Fourier transform. If you take concentration to be C, and if you are in Fourier space, so you can see that suppose if I have C tilde, right, if I have a C tilde, then d by dx of C tilde is nothing but I k C tilde. So, if I take the composition 2 C tilde, then the derivative of the composition is just obtained by multiplying with minus by I k and taking the inverse Fourier transform. So, that is what we are trying to do. So, I take the inverse, so this complex 0 comma I means the complex number which I am multiplying with k. Okay. So, now with this, so we have the Fourier transform quantity. So, if I take this now back, C prime is nothing but real of IFFT of C hat. Okay. So, if I do that, then I calculate the C prime quantity, right. So, now I have C at every point, I have now the del C at every point, dou C by dou x at every point. Now, I can calculate energy. So, I am going to say energy is equal to 0.0. Okay. So, I am also going to do another small test. So, let us split energy into two parts, energy 1 is 0.0, energy 2 is equal to 0.0. So, for I is equal to 1 to n, what are we doing? We are saying that energy 1 is equal to energy 1 plus A is 1, A into A dot star C of I dot star C of I. Okay. Okay, CFI we are doing, so dot star is not required, CFI into CFI into 1 minus CFI into 1 minus CFI, right. So, what is this energy? This is the energy that is associated with AC squared into 1 minus C whole squared. Okay. Now, what is energy 2? That is nothing but the kappa. So, I think I have defined kappa somewhere. Let us make sure that we define the kappa. Okay, I haven't defined kappa. So, kappa is 1. So, I am going to define it anyway here. So, kappa is equal to 1 because later it will be useful. So, kappa into C prime of I into C prime of I. So, this is the second part, end for. So, now I want to write down the total energy. So, energy 1 I want to print, energy 2 I want to print and 0.5 times energy 1 plus energy 2 I want to print. Why 0.5? Because here also it should be 0.5 because there are two interfaces. Remember, there is an interface at quarter distance, there is an interface at 3/4 distance. So, interfacial energy is per unit area or per unit length, whatever. So, we want to get for two interfaces, this is the total energy. So, for one interface it is half the energy because everything is symmetric. Okay. So, we want to get this as the energy. So, I want to print out these three quantities. So, that is what we want to do with this. So, let us go and source interfacial energy CH dot OCT. Okay. So, we are going to see. So, the free energy, if you know the free energy expression, you can integrate it. If you subtract the bulk free energies from there, you will get the excess energy associated with the interface, which is by definition the interfacial free energy. So, using our Korn-Hilliard code, we are just trying to calculate that quantity. So, I got this solution. So, you can see that it forms one interface here and another interface here, but there is some problem in the code. So, let us go find out what is wrong, line 37. Okay. See, I keep forgetting this, C hat of I is complex 0 1 into C hat of I. Okay. So, that is the mistake. So, now probably it will give me the solution. So, we calculated, so the trick that we have used is that the derivative, the dou C by dou x can also be obtained easily if you have the Fourier transform. Okay. it is also going to be very accurate. So, that is another thing, as part of an assignment you will try to do the same thing, but you will calculate the interfacial energy using finite difference formula for the gradient in composition, and you can see how much is the error. The spectral techniques are very accurate. In 1D they are accurate as 1 by n, in 2D that goes as 1 by n squared, whereas in the case of finite difference the error goes as h squared. Okay. So, now okay, there is something wrong. So, line 44, okay, I need to find out. First thing it was, okay, so this I do not want that high, okay. I did not get what the problem was. So, let us run again. Okay. So, there are also ways of solving in 1D at least some of these things analytically and getting to the solution, which is what we will do in the next lecture. Okay. So, in this part of the lecture we have done everything numerically, and we are going to do it analytically in the next one. Okay, line 44 there is a problem. Okay, A was not defined. That is a problem. Okay. So, A was also not defined. So, let me define A also here, A to be equal to 1, because that is what we have used in the, sorry. So, I ran the, okay. But one more thing that you can notice is that the Fourier transform technique is also really fast. That is because it allows us to take larger delta t. Fourier transform itself is not easy, so it is a costly thing to do, but after you do the Fourier transform you see that the solution is very fast because we are able to take larger delta t. So, the interface, the red line is the initial one, and you can see that most of it kept at bulk, A rich and B rich region, but where the interface was, where I put a very large gradient, in one grid size, it went from 0 to 1. Now, it has made it to be a smooth function. So, there is a gradient here, but it is not making a gradient from here to here. That is because even though gradient term will be very small, the bulk free energy density contribution will be very high. It is not preferring what I gave either, because even though the bulk free energy density was 0 everywhere, in this part the gradient energy gave a very large contribution. So, it made an adjustment between the two and it gave me the solution. Now, if you look at the solution, you can see that no, there is something wrong with this. So, the second term also should be 0.1666. So, the total energy should be 0.3333. Okay. So, I do not know where the mistake is, let me find out. So, we took the Fourier transform of C and we calculated the del C, and we calculated C prime as this. Okay. So, probably I should plot C prime and C. Okay. So, I know what the mistake is. So, energy 2 is equal to energy 2 plus, okay, I am not summing it up, I am just taking some energy 2 plus, right. So, that is a mistake. Okay. So, now I think we will get the right solution finally. And the solution when you get, so you can show when we do the analytical solution, we will be able to show that for the F0 that I have chosen, for the kappa A I have chosen, the interfacial energy is 1/3, okay, 1/3, and you can see that that is what the solution we are getting. What is more interesting is that you can see that the contribution that comes from F0 is exactly equal to the contribution that is coming from kappa del C squared. That is how the system is actually finding out the interface that it wants to have. How does it determine what is the interface weight? Either you have F0 of C giving large contribution, or the first profile I made where all the contribution to interfacial energy came from delta C. So, it will keep reducing the contribution from delta C by making delta C to be smaller and smaller. In the process, the F0 contribution will keep going. The calculation will stop when both the contributions become equal. Okay, so that this we can show analytically, which we will do later, but at this point all you need to see is that the contribution between the two is exactly the same. Now you can see what happens. So let us do one small experiment before we stop this lecture. Let us take kappa to be equal to 2 and kappa to be equal to 4. And then see what happens to the solution. So let us go back to the code. I want to put this A and kappa at the beginning itself, so we do not want to put them here because it is very useful to have it here itself. Let us define kappa and A, and in the solution also let us put the kappa and A. So this is dt. So g hat, when it is calculated, it should be 2 times A times delta C, right. So this is where A goes in, and this is where kappa goes in. It is 2 times kappa times k power 4. Okay. So now we have kappa equal to 1. So let us run and make sure that our code is working fine, and then we will change kappa. Let us make kappa to be 4 for example, and see what happens to the interfacial energy and interface width. So both we will look at. Okay. So we get this 0.3333 is the energy, and you can look at the profile, and so you can look at the profile. The profile is like this, right. So it is somewhere between 23, 24 to some 40 or something, right. So that is the interface. Now let us take this thing and make kappa to be equal to 4. Now because we have increased kappa, then the gradient contribution is going to become more. So what should the system do? So that is what we are going to check. So we have increased kappa, so the kappa contribution is going to increase, and we know that interfacial energy should be in such a way that both the kappa contribution and F contribution should become equal. So what happened? You can see that it increased. Okay. Now this is 0.33, 0.33, so it has become 0.6. So when you increased kappa 4 times, interfacial energy became 2 times. So it goes as root kappa. In the same way, and you can look at the profile, and so I do not see the plot. Okay. So you can do this exercise and look at the plot of the okay. So there is a clear figure here, so which I introduced, I do not know for what. And similarly, you can also change the interfacial energy by just changing A. Instead of taking A to be 1 for example, you can take A to be 4, then the contribution from the bulk free energy density is going to increase. So, kappa also should correspondingly adjust in all cases. I mean, whatever be the A kappa that you take, the contribution that comes from F0 term should be equal to the contribution that comes from kappa del C squared term to the free energy. So, that is the thing that we will show later. So, now you can see that the interfacial width also has increased. So, it has gone beyond 40, whereas previously it was only up to 40. Okay. So, you can play around with A and kappa. So, I will stop at this point. We will come back and we will look at some of the analytical solutions and analysis of the solution, which we will do in the next lecture, which will give us a much clearer picture of what is happening in the phase field model. Then we will move on to 2D, and most of this course will be done on 2D systems only. Okay. Thank you.